We have seen that given an experiment, a sample space is a set that has all the outcomes of the experiment. For example, if we toss a coin, then this could be a sample space, tail or head. We have seen the set powers of omega, which is the set of every subset of omega. In this case, power of omega would be the empty set, the set whose only element is t, this set, and this set. Then every element in this power set of omega is going to be called an event. And essentially, an event is a subset of omega. And we can say that power of omega has all the events. Then we're going to define a probability on omega just as a function that goes from power of omega to the interval 0, 1. That means that the function can only take values between 0 and 1, and it takes any event and send it into a number. Then an example of a probability on this sample space could be, we can assign the probability of the empty set to be 0. We can assign the probability of this set to be 1/3. We can assign the probability of this set to be 2/3. And we can assign the probability of this set to be just 1. But not every function from the power set to the interval 0, 1 defines a probability. It must have some properties. For example, the probability of the empty set must be 0. The probability of the whole sample space must be 1. And if two events are disjoint, that means that if we have E, an event, and another event F, and the intersection is the empty set, if they don't have elements in common, then we're going to request that the probability of E union with F is equal to the probability of E plus the probability of F. And we can check that this example satisfies all the properties. Let's do another experiment. Let's suppose the experiment of rolling a die. In this case, we can take as the sample space the set 1, 2, 3, 4, 5, 6. And if we think about all possible events, the set power set, this set will have the empty set, set number 1, and it will have too many to list here. Actually, not too many. It will have 2 to the 6 equals 64 elements. And the observation that I'm going to point out is that to define a probability, we don't need to define the probability in every one of the 64 events. We just need to define the probability on these sets. It's probability of 1, probability of 2, probability of 3, probability of 4, probability of the event whose only element is 5, and the probability of the event whose only element is 6. And the reason is that because when we assign these probabilities, every other subset, for example, the event 1, 3, 5, which corresponds to the event that you roll and add number, then this probability can be viewed as the probability of 1 union with the probability of 3, 5. And these two events are disjoint, then this is the probability of 1 plus the probability of 3 and 5. And this event 3 and 5 can be viewed as the union of the set 3 with the set 5. But because of the property for a probability, this would be the probability of 1 plus the probability of 3 plus the probability of 5. And if we know these three probabilities, then we can find the probability of this event. Doing a similar argument, we notice that if omega is finite, then this works when omega is finite. Then we only need to define the probability of every event with only one element. We don't necessarily have to assign the probability to this one to be 1/6, 1/6, because we may have the situation in which the die is loaded. For example, we can assign this probability to be 1/12, 3/12, 1/6, 1/6, 1/6, and 1/6. When we are doing this, we want to make sure that the sum of all these numbers must be 1, because remember, the probability of the whole sample space must be 1. This is one of the conditions that we require. Remember, the other condition is that the probability of the empty set must be 0, and also that if two events are disjoint, then the probability of the union must be equal to the probability of E plus the probability of F. Notice that disjoint means that the intersection is the empty set, that they don't have elements in common. One observation is that the intersection of two sets sometimes is denoted like EF without nothing. This is also denotes the intersection. Let's check that we have here that this is equal to 1. We have 1/12 plus 3/12 is 4/12, which is 2/6. Then we have 3/6, 4, 5, 6, 6, which is equal to 1. Therefore, this is going to define a probability. Remember that if we define the probability in every event with length 1, then we have a probability in every event in general. For example, the probability of this event, which corresponds to the event we roll the die and we got an odd number, is going to be equal to 1/12 plus 1/6 plus 1/6, and this is equal to 5/12. Then the probability of the event 1, 3, 5 is going to be 5/12. We can also define the probability of getting an even number. Let's say the probability of 2, 4, and 6. In this case, this should be equal to the probability of 2, which is 3/12, plus the probability of 4, which is 1/6, plus the probability of 6, which is 1/6, and this is 3/12 plus 2/12 plus 4/12, and this is 7/12. Notice that since these two events are disjoint, the probability of the union, which is the whole sample space, should be 5/12 plus 7/12, which is equal to 1. We have seen that if we have two sets A and B, then the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection. Because of this property, it is not difficult to show that in general the probability of the union of two events is equal to the probability of E plus the probability of F minus the probability of E intersection with F. Notice that this goes along with the axiom that if the two events are disjoint, then the intersection is the empty set, then this probability is 0, then the probability of the union is just the sum of the probabilities. This formula somehow generalizes the probability of the union when the two events may not be disjoint. In general, this diagram will be useful. If we have two events, let's say event E and event F, then we can think that this region, elements in this region has a probability X, elements in this region has a probability Y, and elements in this region has a probability C, and elements in this region has a probability W. This is called Venn diagram. And then this property essentially says that the probability of the union, which is these three elements, X plus Y plus C, is equal to the probability of E, which is X plus Y, plus the probability of F, which is Y plus C, minus the probability of the intersection, which is Y. We can check that these two things are the same. Let's do an example that shows how this Venn diagram could be useful. Let's suppose that we have that Maya has two books, let's say book 1 and book 2. She takes these two books to vacation, and it's known that she will like this book with a probability of 0.5, and she will like this book with a probability 0.4, and she will like both books with a probability of 0.3. The question is, what is the probability that she will like neither? In this case, if we do the Venn diagram, this is the same. This is book 1, this is book 2, and then we have that this region is, the probability of this region is X, the probability of this region is Y, the probability of this region is C, and the probability of this region is W. Then in this case, we have that book 1, we have that X plus Y must be 0.5. We have that book 2, the probability that she likes book 2 is Y plus C, and this is equal to 0.4. And the probability that she likes both, that means that Y is 0.3. And then the question is, what is the probability that she likes neither? She likes neither, that means this region that has probability W. In this case, we can solve for C. Notice that since Y is 0.3 and Y plus C is 0.4, we have that C is 0.1, and from here X plus Y is 0.3, and we know that Y is 0.3. Then we have that X is equal to 0.2. Essentially, we solve a system. And also the other equation that we have is that the probability of the whole sample space must be 1. Then we have that X plus Y plus C plus W must be 1, but X is 0.2, Y is 0.3, C is 0.1, plus W must be 1, and this is 0.6 plus W is equal to 1, which means that W is 0.4. That means that the probability that she likes neither is 0.4. Let's suppose that in a town there are 3 newspapers, 1, 2, and 3, and this is the information that we know about those newspapers. 10% reads newspaper 1, 30% reads newspaper 2, and so on. Here are the questions. What percentage reads only one newspaper? Percentage that reads at least 2, a percentage that do not read any. Let's solve this problem. Then the idea is that we're going to do a Venn diagram to get all the information. Let's see. In this case, we have to draw the 3 sets and having all the possibilities. The way to do that is in this way. When we do that, we get 8 numbers. X, this is the probability of this region. Let's suppose that this is newspaper 1, newspaper 2, newspaper 3, then we have X, Y, C, and W, U and V, and then R and S. Let's see what information do we have. 10% reads 1. That means that X plus Y plus C plus W is equal to 10%, which is 0.1, and 30% reads 2. Then that means that Y plus C plus U plus V is equal to 30%, which is 0.3. And we have 8% read 1 and 2. 1 and 2 is these two regions. Then we have that Y plus C is equal to 8%. This is 0.08. What else do we have? 2% read 1 and 3. We have that 1 and 3. 1 and 3 is W plus C should be equal to 2%, 0.02. Let's continue with the questions. What else? 1% reads 1, 2, and 3. 1, 2, and 3 is this region here. And then we have that C is 1%. What else do we have? 5% reads 3. 3 is W plus C plus V plus R. This is 5%, 0.05. And 4% reads 2 and 3. 2 and 3 is C plus V is equal to 4%, 0.04. And notice that the other equation that we have is that the sum of all of these X plus Y plus U plus W plus C plus U plus V plus R plus S must be equal to 1. But then we have all these equations, and let's try to solve the system. From here we get that C is 0.1. From here we get that Y, if we combine these two, we get that Y is 0.07. And from here we get that W is 0.01 as well. From here we get that X plus Y 0.07 plus C, which is 0.01, plus W, which is 0.01, is equal to 0.1. And then that means this is 0.09. That means that X is 0.01. What else is missing? X, Y, C, W, U. Let's see, from here we can get that V is 0.03, because C is 0.01, then V is 0.03, and from here we get that 0.01 plus 0.01 plus V 0.03 plus R is 0.05. That means that R is 0. And finally, from here we get that Y is, what is Y? 0.07. And replacing here, plus C, which is 0.01, plus U that we don't know, plus V is 0.03. This is an R. And this is equal to 0.3. But this is equal to 0.11 plus U equals 0.3, and that means that U is 0.19. Now we can do part A. Part A is percentage that reads only 1. Notice that this region X includes people who reads only 1. This region U includes people who reads only 2. And this region R includes people who reads only 3. Then the answer for part A would be X plus U plus R, and X is 0.01 plus U, which is 0.19, plus R, which is 0. Then this is 0.2. Then in this case, the answer is 20%. Percentage that reads at least 2. At least 2, it means at least 2 would be YC, Y plus C plus W plus V. Right? In this region, Y and C, they are reading 1 and 2. Actually, C reads 3, but at least 2 will be Y and C, W and C and V. Then in this case, the answer would be Y is 0.7 plus C 0.01 plus W 0.01 plus V, and V is 0.03. Then the answer would be 0.1 will be 0.12. Then in this case, the answer for part B is 12%. Percentage that do not read any. Do not read any means just region S. This region here. And that region is just 1 minus everything else. X plus Y plus C plus W plus U plus V plus R. Notice that X plus Y plus C plus W is 10%, and U is 0.19, and V is 0.03, and then we have, it will be 1 minus this is 1 minus 0.32, and this is 0.68. That means that the answer for percentage that do not read any newspaper, this region here, is 68%.